Okay, hello everyone. So this lesson is going to be on looking at limits graphically and evaluating limits from looking at a graph. So we'll just get started. I'll start by sharing my screen and we'll go from there. Of course, here we are. Okay, so when we look at limits, in our previous lesson, we just talked about the concept of limits and we looked at slopes of secant lines and tangent lines and tried to see, okay, well, as the slope of the secant line approaches, as that gets closer and closer to a value, it approaches the slope of the tangent line. And that idea, as something got closer and closer and closer to a value, gave us this concept of the limit. As something gets closer to something, it reaches a particular value. So when we look at limits in terms of graphs, what we want to be able to determine is what's happening at a function at or near a given point. So in the previous section, when we just kind of introduced limits, it was about what was happening with the slope of the tangent line near a given point. But now we're just going to look at it right now, just by looking at a graph, what's happening in the graph at or around a particular point. Okay, so one of the things to keep in mind, and you would have seen this in the previous lesson, was specific limit notation. This is actually really important in AP Calculus. So when you do write your AP Calculus exam, how you write your notation is extremely important, and they will take points off if your notation is off. So when we look at limits of a function, how we write them is we just use the word lim, L-I-M, and then the function that is being defined. So if you've already defined f of x previously, you can just say the limit of f of x, or you'd have to actually state what the function is or what the equation is of the function. And then underneath the limit as a subscript, you would write as x approaches c, where c would be any particular numerical value within the function. So x approaches 1, x approaches -5, but that value goes in there underneath the lim expression. And then after you've evaluated it, that is equal to L. Okay, so that notation is expected from here on out. That's how we express limits. Okay, and just watch any sort of conservation of equalities, right? It has to be the limit of a function equals a value. The limit will need to be included in every single one of your steps in order to be correct. Okay, so we read this particular expression as the limit of f of x as x approaches a particular value c is equivalent to L. Okay, so what we're going to be looking at today is just focusing on looking at the graph of a function and getting that visual representation of what's happening at various points. So this is where graphing software is definitely going to come in handy. So whether that is using your graphing calculator like a TI 80 something, or whether that's just opening up Desmos.com. I did post the links to Google Classroom for Desmos. If you're not familiar with that, it's pretty easy online software to use to just graph stuff. But looking at the graph is certainly extremely helpful. And again, on the AP exam, you have a calculator section and you have a non-calculator section. So we will also be looking at how to evaluate limits algebraically in case you have to evaluate them in a non-calculator section. All right. So in some cases, your limit of a certain point is just equivalent to the value of the function at that point. So sometimes you can just take the x value, plug it into the function and say, well, that's where the limit is. That's the value of the function there. So obviously that's where it approaches. Where limits can get a little bit more interesting is what happens when the function doesn't exist at a certain point. What if there's an asymptote there? What if there's a point of discontinuity that's there? If you've got this kind of piecewise function where your graph is at a bunch of little pieces, and we'll look at those in a minute. What does the limit tell us then? Okay, so that's where we are kind of focusing our limits with. So let's consider a pretty rational function. So if we look at the function f of x is equal to x squared minus 1 all over x minus 1, if you looked at your domain, we would have to say that the function doesn't actually exist at 1, right? Because if we substituted a value of 1 in here for x, we end up causing a denominator being 0, and we wouldn't actually be able to evaluate the limit at that point, right? If we tried to substitute 1 into this function, we wouldn't be able to do that. So a couple ways you could then determine, well, what is the function doing close to that point? So the function might not exist there, but we would like to know, well, what's it doing as we approach that point? Option one would be to look at a table of values and actually evaluate the function as you get closer and closer to 1. So evaluate your function at 0.9, evaluate it at 0.99, evaluate it at 0.999, evaluate it on the other end as well, right? So in the last lesson, when we looked at the secant lines, we looked at values that were above points. We looked at points that were above point P, and then we looked at values that were below. So same thing here, you'd evaluate it from both sides to see if you are approaching the same point or maybe you're going in different directions. So again, you could evaluate at 1.1, at 1.01, and at 1.001. So that would be one way you could do it, just graphically, or not graphically, but tabularly. You could also just graph the function and see, well, what's happening around that spot. And then algebraically is another way, which we'll do in a different lesson. So just to show you how we could do that, I am going to bring up Desmos just for a minute. So go over here. We're going to open up the graphing calculator, and I'll share that screen with you as well. Okay. So this is just logged into desmos.com. So the function we were dealing with, I'll just type that in here, f of x is equal to x squared plus 1. And that was all over x minus 1. Okay, so it was x squared minus 1 over x. Let me edit that function. Okay. So when we actually look at that particular graph, it seems as though it's just a linear function, right? But if we carefully look at what happens to this graph, just by kind of touching on that function, at the point 1, you'll notice that it creates this open circle, right? Indicating that at that particular point, our function is undefined at that value. All right, so Desmos doesn't typically show your points of continuity, so just be mindful of that. But it will show it that way. You can, in Desmos, show, look at graphs like tables of values. So you can create a table, right? So you can just, as you can see here, just hit the settings button, click on this create table, and you can just evaluate some points, right? So I could go and say, okay, I'd like to see what the function is doing at 0.9. I'd like to see what it's doing at 0.99. I'd like to see what it's doing at 0.999. I want to see what it's doing at the other end. So what's it doing at 1.1? What's it doing at 1.01? What's it doing at 1.001? Okay, so looking at those points, we can look at the table and see, okay, well, as we seem to be getting closer to the 1 value, our function value seems to be getting ever and ever closer to the value of 2 from both sides, right? As we approach it from the left, we seem to be getting closer and closer to 2. As we get closer to it from the right, we also get closer and closer to 2. And even just looking at the graph itself, you can say, oh yeah, as my function kind of gets close to 1, right? As my x value gets close to 1, my function does seem to get close to 2. All right, so that's what we would be taking a look at in terms of limits. The function might not exist there, but the values could be approaching a particular numerical value. All right, so we're going to head back to the notes. Okay, so I just showed you what that function looked like there. And it is undefined at that particular point. So again, your graphing softwares may not actually show you specific holes in the graph, but you just looking at the domain of the function saying, well, where could this not exist? Just be mindful of what could be happening there. So the other thing to mention when it comes to looking at graphic limits is that there's a concept of one-sided versus two-sided limits. So we can just evaluate the limit from one side, so the right-hand side or the left-hand side. And we'll again see an example here in a minute to show what that kind of looks like. But if we're going to denote a one-sided limit, again, the notation changes slightly. So you'll notice here that if I'm denoting a one-sided limit, the value that I'm evaluating the limit at has either a superscript of a negative or a positive. Okay, so this is just saying the limit of the function f of x as x approaches point C from the left would be equal to something. And this would denote that the limit of the function as x approaches C from the right is equivalent to a value. Okay, so we do have certain piecewise functions, right, where you have a graph that's got just multiple pieces where a right-hand limit and a left-hand limit, I just shouldn't say are not exits, sorry about that, but they may exist or they may not exist. Okay, so you might have one where a right-hand limit exists, but because the graph kind of stops there, the left-hand limit doesn't exist. You may have ones where the left-hand limit exists and the right-hand limit exists, but if they don't equal each other, then the overall limit at that point doesn't exist at that point. Okay, so that's the idea of this one-sided limit theorem that says a function f of x has a limit as x approaches C if and only if the right-hand and the left-hand limits at C exist and they're equal to each other. Okay, so again, this is mathematical notation for that if and only if statement, that this statement is true if and only if these statements are true, right? So this is again showing you that your limit of the function as x approaches C from the right is equivalent to a value L, which is equivalent to the limit of f of x as x approaches C from the left. And if those two things are equal, then we can say that the limit of the function exists at that point. Okay, so briefly, let's just look at an example. So this would be an example of a piecewise function where you've just got this linear negatively sloped line on the domain from 0 to 1, and you see these open circles, which means the function doesn't exist at that point. So this would be that the function exists from 0, including 0, but not up to, but not including 1. Then you've got other pieces, right? So you've got just a horizontal line of y equals 1 that exists on the domain from x equals 1 up into but not equal to 2, right? Because there's your open circle, so you have a point of discontinuity there. You also have that the function is just equal to 2 when x is equal to 2. So it's just like it fills in this hole, but in a different spot. And then again, two other linear functions from 2 to 3 and from 3 to 4. Right, so this is an example of a piecewise function. And from here, we can then evaluate the limit at various points. So just to kind of show you some examples of what that would look like, we'll just do the following. So if we were to evaluate the limit as x approaches 3 of this function f of x, I'm looking at, well, my x value of 3 is here. What is my function doing as I approach 3? Well, from the left, I seem to approach 2. From the right, I seem to approach 2. They're equivalent, so the limit exists and has a value of 2. I can then evaluate just one-sided limits. So in this case, I'm looking at what's the limit of the function as x approaches 1 from the left. So as there's my x value of 1, as my function seems to approach that from the left, my function seems to be getting closer and closer to 0. So from the left, it's 0. Then I can evaluate the limit of f of x as I approach 1 from the right. So coming from the right, my function seems to be approaching a value of 1. Now, if I've just been asked to evaluate just the limit of the function as x approaches 1, you'll notice that that's where that one-sided limit theorem comes into play. And I notice that the limit from the left does not equal the limit from the right. So I have to say that this limit does not exist. And in calculus notation, we often see that as just DNE. It stands for does not exist. Okay. And again here, so we're looking at evaluating the limit of this function as x approaches 2. So I notice that the function doesn't exist at 2, but that's not what we're looking at with limits. We're looking at what's the function doing as we get closer to 2. So from the left, it appears as though this value is staying at 1. From the right, the function seems to be approaching a value of 1. So even though the value of the function at 2 is 2, the value of the limit at 2 is just 1. At this endpoint of 4, this is where I mentioned how sometimes the graph can just get cut off. So the domain of this function is very much from just 0 to 4. So I cannot evaluate a right side limit, but I can evaluate a left-hand side limit, right? So I can say, well, the value of the function, or the limit of the function as x approaches 4 from the left is also equivalent to 1. All right. So that's just kind of the idea of just looking at the graphs and being able to say, okay, this is what's happening. All right. So a brief lesson that time, but just kind of looking at the graphs and being able to get a visual idea as to what's happening with the graph as you approach a particular value. Again, looking at a table of values can certainly be helpful as well. So, being able to just create that on the side, just algebraically, right? If you don't have a graphing calculator, you could always just graph it with just as, or not graph it, but evaluate it with just a basic calculator, or sometimes just in your head. But you can do that. So after looking at this lesson, what you're going to be expected to do is a set of Delta Math practice problems. And I'm also going to assign you a few questions from the AP Classroom. So make sure you log into that as well and take a look at the little mini quiz that I've assigned. Again, they're really just for practice. They're still mandatory. You want to get comfortable with what those questions are going to look like on that AP exam. But I want you to take a look at those types of questions as well. I will say that with the AP Classroom questions, I've been seeing online that some people have an issue with sometimes the limit doesn't show up and it just says Munder. If that happens, try and just clear your browser or use a different browser, and then we'll go from there.